Awesome. Hello, everyone. Good evening. Gute Nacht. Don't let that dissuade you. Snakes are cool, first of all. And second of all, hiking is the best.
Mm-hmm.
Okay. Oh God, Caroline, no.
Oh
Because
my gosh, yeah, I saw a baby bear when I was in Yosemite.
you know what's always following a baby bear.
Yeah,
Yeah.
A mama
did not
bear.
get too close to it.
Okay, so sick. Before we start, does anyone have any questions? Oh, let me put the link in the thing real fast.
I'll also put the Google Doc link in here. I forgot I copied it and then I forgot to paste it into the chat because I was talking about Yosemite.
Oh, actually, it should already be here somewhere. It's somewhere.
I can put it in the Discord also.
I think I got it, but thank you. Hopefully that's the one. That would be funny if it's not.
I actually was gonna say, I think that might be the one from lecture.
No, 225.
Oh,
was
no,
a
it is.
Friday.
Yeah, you're right.
Yeah.
It is the one.
Sick. Okay. Does anyone have any preliminary questions? Get off to the races. So, question one. Actually, I was gonna add some onto that question, but it's enough already. So, question one. Owls are birds of prey with a divine connection that keeps them safe from harm. This connection is regulated by two genes at different loci. The A allele, capital, codes for a normal owl, while the lowercase a allele codes for a structure that enables a divine connection to Athena. The P allele, capital, codes for yellow feathers that disrupt any such divine connections, while the lowercase p allele codes for a brilliant white feather color. So if two owls that are a true breeding pair at these loci, if there are two owls. Oh wait, never mind. So if there are two owls who are a true breeding pair at these loci, goodness gracious, how many of their children will have a connection to Athena? Does anyone have an answer to this question first? Okay, that's a good guess, Joseph. That is actually something important to identify. So Joseph gave actually the chat disappeared. Ooh, dang it. Joseph gave the genotypes AAPP and AAPP. And these are actually the genotypes of our true breeding pair. So the original parent generation are this. So how many of their children will then have a connection to Athena? Yeah, but it's pretty simple. We know what a test breeding cross guy does. Yeah, so rather than waiting, let's see. We know that this individual only has capital A's to give and only P's to give. So the only possible gametes that they can make are that. And it is similar with this homozygous recessive individual. They can only give lowercase a, lowercase p. So all F1 individuals are going to have this capital A and a lowercase a, as well as this capital P and a lowercase p. So all offspring of the F1 generation. How did you determine the parent? The parent's genotype is given right here. Two owls are true breeding. That means they're homozygous dominant, one individual, entirely homozygous dominant, and the other entirely homozygous recessive. So 100% of the F1 generation are going to have this, excuse me, heterozygous phenotype or genotype at both loci. And so, how many of these F1 individuals have a connection to Athena based on what we know about the alleles? And keep in mind, this isn't just a simple cross. Casey says none, and why would you say so?
Because the big A is normal, the big P is yellow feathers, which is no divinity, as it says in the question. Big P codes for yellow feathers that disrupt any divine connections, and so therefore it wouldn't have any connections to divinity, aka Athena, if those two are synonymous, I'm guessing.
Yes, exactly. Very good. And that is what we call an example of dominant. Does anyone want to finish? What is the second word in this phrase? Dominant. And Joseph, you're also right. Epistasis. This is an example of dominant epistasis. We see, as Casey recognized in the question, that this capital P allele, no matter what the allele combination of the A locus, this capital P allele masks the effect or the condition that is caused by the A allele. So it dominates the A allele, and that's called epistasis because epi means like on top of. And so this epistatic allele is like its effect sits on top of the effect of this allele, which we call the hypostatic allele, because hypo means under. So this is dominant epistasis because we have one dominant allele that is epistatic to or masking the effect of another allele. And so because all of the F1 individuals have this capital P, this dominant epistatic allele, it masks the effect of the normal versus magical owl. So as long as we have a capital P, even if we have an AA, it still would mask it. Exactly, Joseph. And so, Casey got it. 0 epistasis, 0 individuals. So what about the F2 generation? Assuming that the F2 generation is a cross of 2 individuals from the F1 generation. I think only 1 out of 16 would be able to. Well, let's see. We can even do the cross. Okay, so we have our A, P, times an AA PP. Can you see my annotation? So,
Yeah.
okay, thank you. So this can produce an, do we really want to do this cross? We don't. We know that, what is this cross called? It has a special name. We've talked about it a bunch. Starts with a T. You can do it. Thank you. Awesome. This is the test cross, and it produces a very memorable ratio, which is 9 to 3 to 3. That's ugly. To 1. So this 9, and actually it would probably be helpful to do the cross. So 9 of these individuals are going to have dominance at both loci. We have our 9 to 3 to 3 to 1. 9 individuals are going to have dominance at both loci. 3 individuals are going to have dominance at one locus, and recessive alleles at the other. And then the other 3 will have recessive alleles at the first locus, but dominant at the second. And 1 individual will be homozygous recessive at both loci. So let's see their phenotypes. So if we have capital A, capital P, we know because of dominant epistasis that this dominant epistatic allele will create a certain phenotype no matter what the A codes for. So because we have capital P, we're going to have yellow feathers and therefore no divine connection. So regardless of the divine nature of this A locus, a capital P will ensure that a normal owl, non-magical, is the phenotype shown. Here we have the dominant epistatic allele is not present. This is homozygous recessive. So since there is no epistatic allele masking the effect of this allele, we can actually look at this allele this time and see what it says. But because we have the capital A, and that codes for a normal owl, which is dominant to the magical owl, we still have normal owls. Making sense so far? We could use a table, but I'm not going to. And here we have another example of the dominant epistatic allele. So no matter what this is, it's going to be normal. In this case, because we have homozygous recessive, 2 small a's, we do have the genetic capability to be connected to Athena, but because of the dominant epistatic allele, this simply can't happen because we will always code for yellow feathers in this case that disrupt our divine connection to Athena. So we end up with another normal individual. And here, no dominant epistatic allele. So we can look at this other locus and we see that lowercase a, yes, excellent. We have a connection. So Joseph was right. 1 out of the 16 offspring in the F2 generation are magical. Any questions? How did I come up with those genotypes for the ratio? And these ones? No problem. Are you talking about, sorry, where's my invitation? Are you talking about these genotypes?
Yes, I still
Okay.
do a Punnett square for everything.
Yeah.
Because I don't know, like I can't just mental math it like how you did it. I have to do it Bonnie style and like draw everything out.
Okay, that's okay. Do it however it works for you. I have just had a lot of practice, and I know that this is how it works out. And this is kind of like definitional to the test cross. It makes sense that because there's dominance, a lot of the individuals are going to be dominant at both loci, excuse me. It's kind of just something that I've become familiar with, I guess.
Since I don't know how to do it that way, can you just show me real fast how to do it the long way? Like how would you
Yes.
even do a Punnett square with all those different letters?
No problem. Wait forward. Let's. So we have our F1 individuals, AAPP, and then AAPP. And so AAPP can create 4 alleles, or excuse me, gametes. We can have A and P. We can have A and little p. We can have little a and big P. And then little a and little p. And obviously the same
Okay,
holds
so you're
true.
getting those from doing a Punnett square of just that one itself by itself.
Yes, exactly.
Excuse me.
And then we know that these are all the possible gametes that can come out of this. And obviously, because they're both homozygous at both loci, they can produce the same gametes. So then we have these 4, and we put these in a Punnett square against each other. So we have AP, AP, and AP. Oops. And then we have, so this is like one of the parents, probably this one. And then on this side, we have this parent over here. And obviously they produce the same gametes because parent 1 and parent 2 have the same genotype. So A. And then obviously we can make all this together. We get APAP. Sorry, crosses take a moment. Yeah, this is why I don't do crosses, because they take a long time. Easier to do it this way. share the board link. Can I do that? Maybe next time, Joseph, but that's a great idea. Thank you. I'll look into that.
I get the gist of it. So if you don't want to finish, that's
Okay.
that's fine. And so from this is basically how you got the 9:3:1 ratio.
Yeah, from this
Okay.
we see that we have a single capital A and a single capital P in 9 of these occasions. And having a single capital A and a single capital P at least. Oh no, I got rid of the annotation. Oh God. Okay, here it is. We see having a single capital A and a single capital P. There are 9 such individuals that have that. And that's where the 9:3 to 3:1 ratio comes, because we can see how many show dominance at which loci. And yeah, it is also easier to memorize it. So 9:3 to 3:1, this 9 is individuals that are dominant at both loci. This 3 is individuals that are dominant at one, recessive at the other. This 3 is recessive at one, dominant at the other. And this 1 is recessive at both. And yeah, we did the cross. Right. And in the future, I do not have a problem crossing it out for you. I'll find a faster way to do it. Does anyone have any questions about this? There are different kinds of epistasis, and we can do similar styles of question that ask about the ratios for different kinds of epistasis that we see. So if anyone would like to, we definitely can.
All right, cool. So Garrett, do you mind if I share my screen? Okay, perfect. Cool. Okay, so in this question, we are told that in leprechauns, one dominant autosomal gene is responsible for beard presence. So while males are often the only ones who express a beard, females can also be bearded. What is this an example of? Any takers? Not quite X-linked, but that is a good guess. Yes, sex influence. So this is a sex influence trait because males will always, all the males, if they have one copy of the allele for beard presence, then all of them will have a beard. But in order for a female to express beards, she would have to have both copies of the dominant allele. So she just had, even though it's a dominant gene, if a female were to have just one, that means that she would still not express a beard. And so does that make sense to everybody? Okay, cool. And so now we're being asked about like a hypothetical. So if a bearded female and a heterozygous male were to have a child, what is the probability that they'll have a bearded male or a bearded female? And so the first place that we can kind of start with this question is obviously figuring out what the genotypes of the female and male parents are going to be. So does anybody want to tell me what the genotype of the female is? Yes. So she'd be BB, and then the male would be, yep, big B, little b, because he's heterozygous. And the female has to be big B because she is bearded. So that's like the big indicator there. And so I put this box in here just so we could see what's going on. I mean, I feel like we probably know what's going to happen by now, but our cross is going to end up looking like this. And so we know what the genotypes of our offspring are going to be, but we're being asked for the probability of a bearded male or a bearded female. So does anyone want to tell me what exactly we're supposed to do now to find the probability? Yes, so Joseph, you're right. We don't know the genders just from looking at this table, but we do know the probabilities of getting each genotype. And so what we can do is we can say, okay, from here, if we have a male, the probability that we'll have a beard present is 100% because you have, if it's male, then as long as he has one copy of this big B, then he'll express a beard. And so that's just one. But then we have to multiply it by the probability of having a male or a female, because this is asking for the probability of two events occurring. I think the wording that's used in the PowerPoint is like two mutually exclusive events occurring together. And so if we want a male that's bearded, or if we want an individual who's bearded and male, that means that we are going to have to use the multiplication or the addition rule. Yeah, multiplication. So it wouldn't be addition because normally with addition, the key like indicator is the use of either or. So in this case, because we want bearded and male, we are multiplying the probability of being bearded, which we said was 1, by the probability that the child will be male, which is 1/2. And then, yeah, so we're assuming there's a 50-50 chance of being a male or a female. Okay, and so, yes, Garrett in the chat said it. So now we are going to have to find the probability of being a bearded female. So does anybody want to tell me what two numbers we'd use to find the probability of being a bearded female? Yes, so it'd be 0.5 times 0.5. So this first 0.5 came from the fact that in order to be a female who is bearded, you have to have big B, and it can't be big B, little b. So that's half right here. And then the second 0.5 comes from you have a 50-50 chance of being male or female. And so after we have these two values, do you think we're going to multiply them together or add them? Because we have the individual probabilities of being bearded male or bearded female right now. Yes. So we're going to add, like just said, because it says or. And does anybody want to tell me what they get when they solve for this? 3 out of 4. I also got 3 out of 4. So 3 out of 4, which is equal to 0.75. And so that would be the probability of having a bearded male or a bearded female. Does everyone feel okay with that? Is there any confusion? All right, I'm going to take your silence as a sign that we are okay with this question. Okay, so going on to the next question, which again involves leprechauns because we are in the St. Patrick's Day spirit around here. So suppose that, Ori, I think for questions like this, it's a lot about doing practice questions to see like what kinds of things you're going to get asked, and just like having exposure to sex limited versus sex influence traits. And so if we have time at the end, we can go over more if you want to, but the textbook, like the suggested homework problems from the textbook, are some pretty good ones to look at for extra practice. All right, so suppose that leprechauns can lay gold coins. Female and male leprechauns can have the gene for laying gold coins. Yes, Garrett.
Hi, thank you. I just wanted to remark that many, or hopefully most questions will like articulate the specifics of the sex limitation for that particular trait.
Mhm.
Like we probably don't inherently know that heterozygous female leprechauns are not going to display the trait versus homozygous females are. So most questions will give you a hint as to which genotypes for which sexes actually display the traits you're looking for. Just keep that in mind.
Yes, that is true. Most of them will be much clearer. We are amateur question makers, so sometimes we might not be clearest when asking.
Well, Sam makes the best questions.
Oh no, you're too kind to her. You make the best questions. Yes, also, yeah, Joseph is right. Also, the gender ratios can be an indicator. All right, so suppose that leprechauns can lay gold coins. Female and male leprechauns can have the gene for laying gold coins, but only males will actually lay gold coins. A female leprechaun can never lay a gold coin. What is this an example of? Yes, so it's a sex-limited trait. And the reason why it wouldn't be sex-linked is because if it were sex-linked, then, oh, well, that's a good point, Casey. So if we were Y sex-linked, then we could say, yeah, so yeah, if it was Y-linked, then it would be sex-linked. So I should have specified that it was autosomal. I'll type that in. But in this case, I was looking for sex limited, but you are very much right. It could be sex linked. Could be. It could be Y linked.
What would be required in like a pedigree, for example, for it to be obviously Y-linked?
So that's something, Garrett's right. You'd probably have to look at a pedigree in order to actually determine whether or not it's Y-linked. But Casey, you were like 5 steps ahead of me. I hadn't thought about the fact that I didn't mention it was autosomal. So Joseph, yes, if it's Y-linked, only males will get it, and typically it does not skip generations.
Well, what I was looking for is that all males will have it.
Yeah. Oh yes, all the males will have it.
Yeah. Sorry for
Okay.
interrupting.
Oh no, it's okay. All right. How do we feel about that one? So that's kind of like how you differentiate between sex influenced and sex limited. With sex limited, you are not going to see it in both genders. You're not going to see it in males and females. It typically is just like one. Whereas sex influenced, you'll see it in males and females, but there's a chance, the likelihood is that like more females than males will show it, or more males than females. And with sex limited, it could skip a generation, but it's not like definite that it'll skip generations.
Because it relies on the proportion of offspring that have a certain sex. Like if you have sex-linked, for sure, skip generations.
If it's recessive.
Yeah.
So sex-linked, if it's Y-linked, then it won't skip generations. Every single male, like Garrett said, will display the trait. But if it's X-linked recessive, then typically it's like in every other generation thing. But if it's X-linked dominant, it doesn't skip generations. Does that clear that up, Casey? Okay, cool. Does anybody else have any other questions about sex limited versus sex influenced? Okay, cool. If not, Garrett, do you want to take over the next question?
Sure. Actually, I have a question for you all. So if, for example, you had, actually, never mind. So let's just move on. So question 4. In Enderman, whether or not ender pearls break when they're used. Sorry, if you don't play Minecraft, this may be like unfamiliar, but just try to go along with it. In Enderman, whether or not their pearls break when they're used results from a genetic maternal effect. An autosomal allele for breaking pearls is dominant over the allele for pearls that resist breaking when used. An Enderman named Elisa has break-resistant pearls and reproduces as a female. So since they're a female, they might exhibit the maternal effect. Are the following statements true or false? For each statement, is it true or false? Any ideas for statement A?
I'm curious
take your time.
why. I'm curious why the allele for pearls that resist breaking is B star as opposed to little b.
It's just the terminology. It's could be B plus, could be B star, whatever. As long as you like have a distinction.
Is it recessive or is it also dominant?
Regular B is dominant to B star. And Elisa has break-resistant pearls. So we have true. I don't think A is necessarily true. True, because it, Joseph has it. Very good. We cannot tell Elisa's genotype based on solely the information that Elisa has break-resistant pearls, because the genetic maternal effect is the reality that a mother's genotype influences their offspring's phenotype. Elisa is obviously the offspring of Elisa's mother. And we don't know Elisa's mother's genotype. Elisa's mother's genotype influences Elisa's phenotype. We only know Elisa's phenotype. We don't know Elisa's genotype. So we can't say for sure whether or not it's B star, B star. Because yes, Elisa has break-resistant pearls, but Elisa's genotype could be that they have breaking pearls. They only have break-resistant pearls because Elisa's mother's genotype was B star, B star. So very good, Joseph. What about B? Did that make sense, by the way? That explanation? It's kind of the foundation of maternal effects. Exactly, Ori. Once again, we don't know Elisa's genotype, and we can't infer it based on Elisa's phenotype. So once again, B is false. I should say that. False. But from this, we would know the mother's genotype for sure, exactly. And it wouldn't be ambiguous because break-resistant pearls are dominant or recessive? Recessive, exactly. And so the only way to be recessive is to have B star, B star. So we know that because Elisa displays this phenotype is because Elisa's mother had the corresponding genotype for break-resistant pearls, which is homozygous recessive B star, B star. So what about C? All of the offspring produced by Elisa must have break-resistant pearls. Joseph says false. And why is that? Why do you think so? Because her genotype is unknown, exactly. Once again, we don't know Elisa's genotype. And because of the genetic maternal effect, the fact that Elisa reproduces as a female, Elisa is a mother to Elisa's offspring. And the phenotype of the offspring of Elisa depends on Elisa's genotype, which, once again, we don't know. So this is false because we don't know Elisa's genotype, and therefore we cannot know the phenotype of their offspring, which would be affected by the genetic maternal effect that Elisa levies onto them, for lack of a better word. Wait, wouldn't she have maternal effect on her offspring? Exactly, she would have, or excuse me, Elisa would have maternal effect on their offspring, but we don't know Elisa's genotype. Elisa has break-resistant pearls because Elisa's mother's genotype coded for break-resistant pearls. Elisa could have breaking pearls, which means that, or Elisa's genotype could code for breaking pearls, which means that no matter their genotype, the offspring would phenotypically display Elisa's breaking genotype. But obviously we don't know Elisa's phenotype, so we can't make any assumptions about the genotype. Yes, sorry. What about D? Exactly. Once again, I don't know Elisa's genotype. So we don't know Elisa's genotype, which means we can't make any inferences about the phenotype of their offspring. Or Elisa. So what
When
about
it comes
E?
to maternal effect, sorry to interrupt just like that, but when it
Oh, yeah,
comes to
no problem.
maternal effect, it's an all or nothing, correct?
Yes. Let me break out the pen really fast. So we have some organism and they're pink. Their phenotype is pink. Let's say their genotype codes for red. All of the offspring of this pink individual are going to be red because this pink individual imposes their genotype onto their phenotype. All of these individuals share this mother, and therefore the maternal genetic effect is imposed on all of the offspring. Okay, I think someone said it. False still, yep. Oh, wait, actually, no, we didn't talk about it. Shit. Okay. So why is why is this what it is? Does anyone know what it is? I definitely didn't give it away. Okay. It's false. Yes, it is false. Why is it false? Can anyone tell me?
We do not know the mother's mother genotype. So we don't know Elisa's mother's mom genotype, because that would be what define if it's break resistant or not.
Exactly. Elisa's mother was also the subject of Elisa's mother's maternal effect. So Elisa's grandmother, the genotype of Elisa's grandmother displayed the maternal effect onto Elisa's mother. So that, the genotype of Elisa's grandmother, is what determines whether or not Elisa's mother had break-resistant pearls. We know Elisa's mother's genotype had to have been B star B star for Elisa to have the phenotype that corresponds to B star B star, but we can't tell Elisa's mother's phenotype because that relies on Elisa's grandmother's genotype. So many mothers. Yes, Alec, exactly. Because we don't know Elisa's mother's phenotype. Well, we do know Elisa's mother's genotype. That's what made Elisa have this phenotype. But okay, so part F, what do we think? The one true, exactly. Who can tell me why? We have mentioned it. Exactly, all or nothing, Ori. Joseph asks, why isn't Elisa's mother have break-resistant pearls? So let's draw it out. And her pearls are like a really dark shade of green, greenish blue. So I don't have that color, but so let's say we have Elisa's mother. And Elisa's mother's phenotype is a mystery. We don't know it. Elisa's mother codes for, like her genotype is that it codes for break-resistant pearls. B star, B star. Pretend those are stars. And so Elisa, because Elisa's mother levied the genetic maternal effect onto Elisa, Elisa displays the break-resistant pearl phenotype. However, we don't know Elisa's genotype. Wait, was that your question? Why isn't Elisa's mother have break-resistant pearls? Because, well, Elisa's mother could have break-resistant pearls, but because of the genetic maternal effect, Elisa's grandmother was the one, Elisa's grandmother's genotype gave Elisa's mother their phenotype, their characteristic, which in this case would be whether or not the pearls resist breaking or break when used. And the only information we were given was that Elisa has this phenotype, which obviously they got from from Elisa's mother's genotype. Did that, I feel like I whipped around and, but if Elisa has that phenotype, why does her mother not have it? Elisa has this phenotype, why does the mother? Oh, because the genetic maternal effect is about how you never asked the mother's genotype. Exactly. Oh wait, but if Elisa has that phenotype, why does her mother not have it? The mother has the genotype that corresponds to Elisa's phenotype, but the genotype of an individual, for example, Elisa's mother, the genotype of an individual does not dictate the phenotype of that individual. It is the genotype of their direct maternal parent that influences their phenotype. Yeah, it's like delayed action. No problem. And someone else had a question, or no, that was Ori answering it. Yes, so this is true for the same reason that my previous pink illustration is true. Because all siblings share the same mother, the mother's genotype doesn't change. So the mother will impose the maternal effect on all of their offspring. So if this is Elisa right here, Elisa's siblings will also have the same phenotype as Elisa, which is break-resistant pearls. All right. Any questions? So if we ask for Elisa's mother's genotype, it would be for break-resistant pearls. Exactly. Elisa's mother's genotype is what gave Elisa their phenotype. Yeah. Yeah, it's kind of like,
One way to think about it, sorry, Garrett, to interrupt, but like it's like a one generational lag.
exactly, yeah. Like you have a yellow person or a yellow individual, they have a yellow genotype. Actually, no. So you have a yellow individual, they are yellow, is their phenotype, but they have a red genotype. They aren't going to display that red genotype because they're yellow. Instead, it's going to skip to their offspring who are going to have the red phenotype, but the red phenotype person, for example, might have the blue genotype. And so their offspring are going to display a blue phenotype because of their blue genotype. And let's say that this blue individual had a dark, I guess that's a brown genotype. So their offspring is going to have a brown phenotype. Just like Sam said, it's like they're passing on, that's not a good way to say it. It's like, actually, I'm not going to get into that. So let me ask you this. Can we tell Elisa's father's genotype? Nope, exactly, because it is the genetic maternal effect, not paternal. So we cannot make any inferences about Elisa's father's genotype or phenotype based on this information about Elisa, because fathers simply aren't as important. Oh my God. Yep. Speaking from experience. Hey, oh, okay. Next question. Let me clear this.
All right. So let me share my screen. And here we are. So rounded ears are an X-linked recessive trait in leprechauns. When a population of 176 leprechauns was taken, I should have said was surveyed. Sorry, I made these questions at 6 a.m. When a population of 176 leprechauns was surveyed, 36 males were found to have rounded ears. What is the allele frequency and what is the genotypic frequency? Yes, Ori, what is your question?
So I don't know if I'm getting a bit ahead here, but I do remember that for allele frequency, we do have to know if it's if it's a haploid or diploid, correct? So I don't know if we went over how to go about finding allele frequency with an X-linked trait. And I was trying to think about it ahead of time, but I was like, I don't know what to do.
So we will go over, I can walk you guys through this because I don't think we went over an example in class yet that dealt with Hardy-Weinberg or like, yeah, so this kind of mixes Hardy-Weinberg equilibrium with finding allele frequency and genotypic frequency. And so I will walk through it with you guys. So basically, we know, just like, no, let's do it. Okay, so basically, we are told that rounded ears are X-linked recessive. That's like one of the big things to take away. And then we're told that 36 males were found to have rounded ears out of 176. And so we know that males are XY, right? And so since males are XY, that means that they only have one X allele because there's only an X and there's only a Y. And so if we have 36 males who have rounded ears, that means that the prevalence of the rounded ears allele would just be 36 divided by 176. Does that make sense, or should I go over it again?
If you wouldn't mind going over it one more time, I would appreciate it.
Oh yeah, no problem. Okay, so our males are XY and we have 36 males who have rounded ears. And so that means that 36 of our alleles out of the whole population of 176 are going to show the recessive X-linked trait for rounded ears. If we were dealing with, suppose it was like X-linked dominant, then it'd be like a whole different thing. But because it's X-linked recessive, that means because it's X-linked and because we're dealing with males, we are able to assume that the frequency of having rounded ears would be 36 out of 176. Because the males would be X R, oh, I don't know how to do the superscript in Google Docs, XR Y. And so if we have 36 males with round ears, then that means that, oh, is it control 6? I don't think it's control 6, but it's fine. We'll just roll with it. And so because we have 36 males with round ears, also not control shift 6. It's all right. We'll live with it. And so that means that if you use like the formula from class, then that would be like saying that there's n individuals over, or like n individuals who are affected over the total. And so we would just have 36 who are affected. So that would be n affected divided by n total. Okay, so for us, that would be 36 who are affected divided by 176, which is the total. I should have just started with the formula to begin with. I feel like that probably would have been easier.
So when we don't have to take into account the second N of the heterozygous. question mark?
So, well, this is where it gets kind of hairy. So, no, not for when we're dealing with X-linked recessive traits.
So X-linked recessive, or like, yes, for this specific case, we are, because there's no such thing as heterozygote for this specific example.
Oh gosh, maybe I didn't think this question out well enough. All right, let's just pretend that this is recessive. Are a recessive trait in leprechauns. And so let's start over from scratch. I feel like the X-linked is really throwing us off. So we'll just trash the X-linked. All right, so starting from scratch, we are dealing with just a recessive trait, and we have a population of 166 leprechauns, and 36 males were found to have rounded ears. All right, so we're just starting from scratch, and we're going to pretend like the last 5-10 minutes didn't happen. All right, so that means that, let's say we're going to use R for our alleles. And so our male is going to have, yes, Joseph is one step ahead as always. So that means that our males, we're going to have 36 RR individuals. And if we look at our good old friend Hardy-Weinberg equilibrium, then we know that P squared plus 2PQ plus Q squared is going to be equal to 1, assuming that we're in Hardy-Weinberg equilibrium. So that means that which of these terms would represent an individual who's little r? Yes, so Q squared, or I don't want to confuse you more and throw you off more, but you could say that P squared is your little r. As long as you keep your P's and your Q's straight, it doesn't matter. But for conventionality's sake, most of the time people say that recessive is Q squared. So now that we know that Q squared would be like the recessive, we can literally just set Q squared equal to 36 and solve for Q. And yes, Garrett, I think it is an idiomatic expression. Know your P's and Q's or something like that. All right, so because we have 36 recessive individuals. Oh my God, 136 out of 176. So we have 36 recessive individuals in our whole population. And then if we look back to Hardy-Weinberg equilibrium, we know that Q squared is the frequency of the recessive individuals in our population. So we can set 36 over 176 because that's the proportion of our population that is recessive, and set that equal to Q squared and then solve for Q. And when we solve for Q, we get so Ori, we changed it from sex linked to just autosomal because I feel like sex linked was really throwing a wrench in. And so we just figured out how to solve for Q. All right, and then when we solve for Q, we should get 0.452 if I put that into my calculator properly. Okay, so I know that was a lot. I could go over it again if we need to.
I have, I think, a question.
Mhm.
So something that's throwing me off a little bit is if we are getting asked about allele frequency, we didn't exactly use the allele frequency formula,
Mm-mm.
and instead
So-
the Hardy-Weinberg formula.
Yeah, so you can find, unless you're like explicitly told in a population, the number of individuals who are big S, or who are homozygous, dominant, and recessive, and heterozygous, that's pretty much the only time that you're going to be able to use the formula. And if you're not told the number of individuals in a population who are homozygous, dominant, recessive, and heterozygous, then you have to turn to Hardy-Weinberg and use that to find your frequencies. All right, are there any other questions about that? And so Q is equal to little r. Okay, so now we can solve for the frequency of big R. And so to do that, we can say big R. So that would just be equal to 1 minus, yes, 1 minus Q, because we'll say it's equal to P. Okay, so P has to be equal to 1 minus Q because P plus Q always has to equal 1. And so if you rearrange P plus Q equals 1, then you can get P is equal to 1 minus Q. And so when we do that, we'll get 1 minus 0.452 and get 0.548 as the frequency for R, or for big R. Okay, how do we feel about that question? I know that Hardy-Weinberg equilibrium can be confusing and a lot. So are there any questions about that? Okay, I'm hearing a lot of silence. So I'm assuming that we're okay with it. If at the end you want me to go over it again, we can also go over it again. So to find our genotypic frequencies, we can once again go back to our good old Hardy-Weinberg equilibrium equation. And so we would just be using the p squared, 2pq, and q squared values and plugging into that. So can anybody tell me what p squared would represent in our situation? Would it be big R, big R, big R, little r, or little r, little r? Yep. So it'd be big R, big R. So that's equal to p squared. And so to solve for that, we would literally just take our p value that we found in the first part and square it. And when we do that, we should get that it's 0.300 would be big R, big R. And then can anybody tell me what R2PQ would represent? Yep, big R, little r. So that would be 2PQ. And then when we do the math for that, we'll get 2 times our Q frequency and then times our P. We should get 0.495. And then we went over it, but I'll ask again. What does our Q squared represent? Yes, recessive. So that would just be little r. And that would be Q squared, which is 0.205. And we can get this by either doing 0.452 squared, or we can also look at what we were given, and we were told that 36 males who have rounded ears out of our, or there were 36 males who had rounded ears out of our 176 leprechauns. So that's another way that we could find our allele, our genotypic frequency for our recessive individuals. And if we did this correctly, 0.3 plus 0.495 plus 0.205 should equal 1 when you add them all together. So that's a handy way of checking your work at the end to make sure that you are doing everything right. But you can only use this part at the very end to check your work if your population is in Hardy-Weinberg equilibrium. So if you're not in Hardy-Weinberg equilibrium, then you cannot check your work this way. And so, Joseph, did you think that these were our allele frequencies? We saw for the allele frequencies up here. Okay, cool. So this is how we would go about solving a question like this. Does that make sense to everybody? So there are two ways that you can get allele and genotype frequencies, and that's either when you're explicitly given your homozygous, dominant, recessive, and your heterozygous individuals in a population. And then we can and then you use Hardy-Weinberg when you're given a question like this. And so, yes, so we can use allele frequencies to find genotype frequencies or genotype frequencies to find allele frequencies. In this scenario, it was the best choice to find the allele frequency first to find the genotypic frequency, because if we were trying to find the genotypic frequency first, we'd only be able to find the genotypic frequency of our little r individuals, but we wouldn't have been able to find big R, and big R, little r, because we didn't know the frequency of big R. And so from knowing the frequency of our little r individuals, we were able to find the frequency of little r, and then using the relationship of P plus Q equals 1, we could find that R is equal to 0.548. All right. Is everybody all right with that question? Okay, I'm hearing no objections or questions. So if we're all good, then we can move on to the next question.
And if you're not okay with Hardy-Weinberg equilibrium, get ready to do it again.
Yeah, there's a lot that we do with Hardy-Weinberg. So definitely practice and make sure that you understand what's going on with it.
Okay, so number 6. In the Southern Water tribe, water bending is coded for by the alleles capital and lowercase w. where dominant capital W can't bend and recessive lowercase w can bend, can bend. If the frequency of the lowercase allele is 0.24, the bending allele, what is the likelihood that a random member of the tribe you select from the population is heterozygous at this bending locus? So what information do we have so far? Water bending is recessive. Yep. So this is recessive. And so big W no bend, little w bend, 0.24 allele frequency for bending, exactly. So this is equal to 0.24. And if we had to familiarize or make this more familiar, we'd say that it's Q. So we have Q equals 0.24. So what can we use that with? Exactly. We know that P plus Q equals 1. We just did a question about it. And this P plus Q equals 1, just in case it's like this thing ringing in your mind that you don't know what's going on. P is the probability or proportion that any one thing is happening. And Q is the probability or proportion that some other thing is happening within the context of this thing happening. So for example, if you only have two options, this is the probability that something is one option. This is the probability of something that something, that something is the second option. And therefore the probability that either thing happens is equal to 100%, 1. Because, out of two things that happen, or if only two things can happen, the probability that one plus the other is going to happen is 100%. It's always going to happen. So just keep that in mind. I got a text, but I'm not sure if it's on. Okay. So P plus Q equals 1. And so because this W is Q, we can look for our P. And P in this case is going to be our capital W, which Ori correctly said is for the non-benders. So we have P and it's dominant. So we have our P, or we don't have our P, but we do have our Q. And that equals 1. So we have W plus 0.24 equals 1. And if we do a little algebra, we get the fact that capital W equals 0.76. So the probability that any one person, actually, I'm not going to get into that. So the question asks, what is the likelihood that a random member of the tribe selected from the population is heterozygous at this bending locus with the W and the W? So we're not there yet. We're not at the answer, but we have the allele frequencies for our two different alleles. And just like in the last question, we can use them now. Exactly, we can use the allele frequency to find 2pq. And so this p and q equals 1 is all about allele frequency. Assuming that there are only two alleles, only two possibilities, when you add them together, they comprise the 100% of alleles. But alleles combine into genotypes. That's how organisms work, how life is enabled, and that's what we study a lot in genetics. So we then come upon the equation of p squared, and if you are ever wondering, you can go to format text superscript. Yeah, but then to undo it, you have to do it again, which is annoying. So, I think there's a hotkey. I'll look into that. P squared plus 2pq plus, I'm going to be cheeky and just copy it so I don't have to go back in. Oh yeah, I'm too clever. So this is what we have for our genotype frequencies. And this also might seem confusing if you don't know where it's coming from. This is our famous 1:2:1 ratio. 1p plus 2pq plus 1. 1, 2, 1. And that's the result of a monohybrid cross. So we have our 1 to 2 to 1 ratio of dominant phenotype, heterozygous phenotype, and recessive phenotype. So we want to know how many, or what is the likelihood, the probability that any individual is heterozygous. So which of these is heterozygous? Which of these 3 genotypes? 2pq, exactly. And so because we know our W, our P, and our W, Q, we can plug them into this handy little formula. So actually, we don't even really have to do that. In order to find 2pq, we simply have to plug in our P, which is our W, capital, non-benders, and our Q, which is our lowercase w, or our benders. And so we have 2pq equals 2, and I'm actually using my phone, and that's where my calculator is. So if someone else could do this math, I'd appreciate it. Middle, exactly.
I got 0.3648.
Thank you. And so this is because we have identified the 2pq, we have therefore identified the proportion of tribesmen in the Southern Water Tribe that are homozygous, or excuse me, heterozygous at the water bending locus. So there is a 0.3648 or 36.48% of people in the Southern Water Tribe are heterozygous for bending. And what does that mean their phenotype is? Non-bender, exactly. So that's that. Oh, and then everything changed when the Fire Nation attacked and enabled the evolution of the genome of this population of water tribesmen. First, the black snow falls, and in the ensuing invasion, the population that was previously 20,000 is decimated. I write these questions. So decimated, in case you didn't know, is to be reduced by or to 10%. So actually that's something I should have articulated. For decimation is reducing to 10% of original value or reducing by 10% of an original value. And in this case, I meant that it was reduced to 10% of its original value. So our population was 20,000 water tribesmen, and now it's decimated down to 2,000. So the proportion of this population that was homozygous dominant was previously 57.76%. But after this drastic reduction, it now exists at 2%. So we have, where was I going with this? Oh yeah, so we have 57.76 of our 20,000 individuals were homozygous dominant. And what is the homozygous dominant genotype? Non-waterbenders, very good, that are WW. And so WW is 20,000 times 57, 0.5776, means there are, wait, do we even need to do this? I'm just going to do it for the fun of it. Actually, I don't have a calculator, so I probably shouldn't do it for the fun of it. Oh, thank you for coming, Caroline. Absolutely. And if you have any more questions, you can ask them whenever. And I was even thinking of making more questions, running through more questions like on a recording that I can post, because we only have 30 minutes left. But yes, thank you for coming. Sam got 1,100, or no, 11,552 numbers. So, homo down. And whenever I get Hardy-Weinberg questions, I just like to list all this stuff out. Like, for example, the number of individuals of a certain genotype. If I don't have the proportion, but instead given the number and the total, I like to find the proportion because, you know, you're probably going to need these values if you're being asked about Hardy-Weinberg. So we have this. It starts like this, but then after the Fire Nation attacks, is now 2,000 times 0.02, which is 2%. And that is equal to divide by 100, multiply by 240 individuals. So we have this information. The proportion. Is this population now in Hardy-Weinberg equilibrium? And how many individuals now are not benders? So in order to find out whether or not it's in Hardy-Weinberg equilibrium, we do need to find the proportions of the different genotypes. So did I even do this? Did I set this question up properly? Actually, it doesn't even matter. So we know that, let's just disregard this. It doesn't matter anymore. The Fire Nation has attacked and there's no going back. So this is our new population. I guess it's not in Hardy-Weinberg because they evolved and population is small now. You're getting there, Joseph, you're getting there. So we have WW, and so we have WW. How can we find W? Square root of WW, exactly. Because WW is kind of like W times W. And we know that W times W is just W squared. Like 2 times 2 is 4, and 2 times 2 is also 4 squared. Or no, you get it. You get that point. Thanks for asking. Absolutely. I'm sorry, Casey. Oh my God. Good luck with your lab report. I just did that last night. But yes, I will see you soon, hopefully. Okay, so we have our WW, and we know that WW exists at 2% now. So WW is 2%. Then W is equal to the square root of 0.02. Because, you know, W squared, in order to get down to W, you need to take its square root. And actually, I think there's even, I'm not gonna try to do that. The square root of 2. I don't know what that is.
I think it's 1.4.
Oh, but what about
Oh,
0.02? Yeah.
Gosh, I hate that I know the square root of 2. Yeah, Ori is right. It's 0.1414.
Okay, so this is the allele frequency for the non-bending allele, capital W. So how can we find the, oh, actually, yeah, that's right. Square root of 2 over 2. That's like cosine 30 or sine 60 or something. Unit circle. Oh my God. But yeah, now that we have the allele frequency for one of the alleles, we know that the combination of the only 2 alleles that we have in this population, W plus W is equal to 1. So now that we have one of these 2 W's, we can do some simple algebra and find that W equals 1 minus W, which is equal to 1 minus 0.1414, which is 0.85. Oh, someone put in the chat 8586. Thank you. 0.8586. So I'm actually going to rewrite that. We have that our W equals 0.0858. Oh wait, not 0. 8586. So whoa, we went from this allele only being 24% of all the alleles that exist in the population to being almost 86%. So this makes sense in the context of biological fitness. Biological fitness is the suitability for one's environment. And if you have, for example, enhanced combat capabilities, you know, a very unique martial art, such as waterbending, and you're constantly engaged in martial conflict, then having this allele, or having the genotype where you can actually bend, is highly beneficial. So individuals that have this are selected for, and therefore in this drastic population reduction, they become more present. Thankfully, they didn't succeed. So actually, I wanted to ask that question. What is this called? This drastic reduction in population that leads to changes in allele frequencies? Death? No, exactly, Alec. It is called a genetic bottleneck. And if that confuses you, I'd be happy to draw it. So we have, for example, it's kind of in like the shape of a bottle, you know, got the little lid here, the little thing here, and it's probably made of glass, so it has that really satisfying like stuff at the bottom you can run your fingers across. Anyway, so we have this large number of individuals that represent the previous population, the previous 20,000. Or get off Discord. Sorry, just kidding. Do whatever the heck you want to do. So we have this large amount of individuals that represent the previous number of individuals. And so we then come across a bottleneck, a specific event that drastically lowers the number of individuals that make up the population. If you want to, I mean, I don't know anything about lab, but if you want to talk about it or ask questions about it, we can try to help. So yeah, bottleneck, drastic reduction in the number of individuals that make up a population. So after this, yeah, you got this. After this bottleneck, we see drastic reduction. Is the population now in Hardy-Weinberg equilibrium? We can test it. So we have the allele frequencies. And to know if something is in Hardy-Weinberg equilibrium, the sum of the genotypes have to equal 1. You know, all the genotypes that exist in the population equal 100%. And that makes sense, because 100% of the genotypes is, you know, all the genotypes. So we have this equation once more. This is our handy little Hardy-Weinberg equilibrium. So we must use p to the 1, yeah, p squared plus, yeah, you got it. We have to use this Hardy-Weinberg equilibrium. And for the sake of this problem, I am going to switch the things around. So we have this. And now that we know our allele frequencies, we can input the numerical values in for the alleles that we see. So we have W squared, which is, funnily enough, 0.02 plus 2 times W 0.1414. Someone please do that math. And it's not 0.0. I keep doing that. Plus W, or lowercase w squared, which is this guy squared, which I also don't know. Someone please do that. I'll be 0.8. 7372. this has to equal 1. So if it doesn't, we know that this population is no longer in Hardy-Weinberg equilibrium, assuming that they were back when they were 20,000 in number. So is this true? Does this number equal 1? It is. Okay. So I definitely set up the question wrong because it shouldn't have been. Yeah, so apparently, according to the numbers, Hardy-Weinberg, oh, then it's not. If it's not exactly 1.0, then it is not in Hardy-Weinberg equilibrium, because that is 100.0001%. Could be a rounding error, perhaps. But if it does not exactly equal 1, then it's not in Hardy-Weinberg equilibrium. Anyway, whether or not it is, someone with a good calculator can decide. I do not have access to that at the moment. So to answer the next question, how many individuals now are not benders? There's an app on the iPhone called Taculator, and it's like one of the TI-84 graphing calculators just on your phone. It's really cool, but I can't use it during tests because, you know, it's on my phone, and I can't use it now because I'm using my phone for Zoom. But so how many individuals now are not benders? Which numbers do we need to determine the answer to this question? In order to identify those numbers, we need to identify the genotypes that correspond to a person or a water tribesman not being a bender. So we can look back at the question. Dominant W can't bend. So if they have a capital W, they cannot bend. So the collection of homozygous dominant individuals and heterozygous individuals are non-benders. And so we have the proportions. So we need to multiply them by the total number of individuals that now make up the population. Joseph was right. It is the WW and 2WW individuals, also known as the homozygous dominant and heterozygous individuals. So in order to find the homozygous dominant individuals, we actually already did that when we found 40 of them. I think that number was right. Not 400,000, 40. I don't know why that happened. And the 2WW individuals. So once again, we can multiply this proportion by the total number of individuals, because this 2WW is the percentage of individuals within the 1 or 100% of individuals that make up the population that have this heterozygous genotype. So we can multiply the proportion of them by the number that they exist in, or by the population that they're a part of, to get the number that they exist in. So whatever this number was, times 2,000. Someone help me. Joseph got 485.6. Actually, that's a good point. Whether or not to round. Do you know the answer to that, Sam? Whether or not you round up? Because, like, obviously you'd get more accurate, but you don't want to, like.
Yeah, so normally when you're dealing with, or like in my experience, when you're dealing with like populations like this, like people or animals, you always truncate. Or like if you're working with like bacteria populations and stuff, you tend to truncate because you can't have like 6/10 of a person. And then to round up would be saying that like you have an extra 4/10 of a person. So like typically truncating is the way to go.
Okay, so Yes, Joseph was right. Sam is right. 485 individuals. So the total number of non-benders in this now 2,000 population is the WWs plus the 2 WWs, which is equal to, 485 plus 40, which is 525. All right. That is true, Joseph. That is exactly true. You could, instead of finding the total number of non-benders, because there's only two choices, bender or non-bender, you could instead find the number of benders and subtract that from 100%. And I guess, why not do it right now? Undo that highlight. So you can find benders minus 1 equals non-benders, which is WW individuals minus 1 equals WW. Did we already calculate that? I don't think so. Oh yeah, we did. 0 point, or no. Well, we calculated their proportion, so we just need to multiply that by 2,000. Someone wants to do that really French. Save me. Well, it wouldn't be actually 1 minus that. It would have to be the 0.73 and then multiply it by the 2,000. Because remember, this 1 is just representing the 100% of individuals that make up a population. So we could do the 0.7372 minus 1 and then multiply that by 2,000. Sorry, yes, sorry, we're flipping back and forth, Joseph. So, yes, WW minus 1 is 2. Actually, my way is a little less confusing. Not that our well, hopefully it equals 525. Yeah, so 0.78, I guess I'll do it myself. Calculator. 0.7372 minus 1. Right, I guess it would be 1 minus that. So 2628 times 2,000. So the proportion of individuals that are not benders times the number of individuals, therefore gives the number of individuals that are not benders. That is 525.6. All right. Nice. So those were all of the good. Those are all the questions that Sam and I prepared for you. Do we have any more?
We have like 10 minutes, so if anybody has anything they'd like to go over again, we could.
Okay, no more questions. What
Right.
about you, Alec?
Wait, Garrett, I'm gonna pause the recording really quick so I can say the secret question. We just like completely sign off or get even more derailed. Oh, Alec is good.
If anyone's
So we can
curious,
keep-
the last national park I went to was Yosemite, I think.
Oh, great place.
What was the question?
How many states have I been to? Oh, wow, a lot, I think. Well, probably not a lot, actually. Like I'm
I
from, oh, what's that?
Oh no, you go, Garrett.
Oh, I was just gonna say I'm from Seattle, and I was born in Seattle, but I'm from California, and um, I've lived in Virginia and North Dakota, and that's pretty much it, except for the one time I drove out to California. I drove through like Kansas and Utah and stuff.
Oh gosh, Joseph, I've seen the National Park stamp book. I saw this girl with one when I was actually at Zion, and I was like, that is so cool. I should get one day. So
They
that
have
I
National
can.
Park Monopoly. Oh my gosh, so cool. If you play Monopoly, I guess it's cool.
I've been to quite a few states also. I think I'd have to look at a map and like count all of them. But over winter break, my family and I, we drove cross country and we went through 14 states.
Whoa.
Yes, it was a good time. How my younger brother, he's still in high school, and so they had a 16-day winter break this time, and we just took like all 16 days and drove. Gosh, actually, Ori, if you could believe it, this is actually the third time that I've done it, and my family has done it a fourth time, but I was not alive the first time that they did it. I've only been here for the last three. Yeah. Oh my gosh. Yeah, me too, Joseph. I traveled more in high school too. Like the past years because of COVID, like haven't really gone anywhere. This winter was like the first time that I had traveled in 2 years. And I was like kind of cool, weird and crazy. I propose that we all just take a road trip.
And if you like haven't done cross country by car, I recommend it. California's awesome,
Mm-hmm. It is.
except it's kind of a climate change nightmare.
Oh yeah. It's a little bit of a mess.
But you know, where isn't a climate change nightmare? Am I right?
Mm-hmm.
We are in winter.
Yep.
Oh,
We're in winter, and on Monday it's supposed to be like 80 degrees, and
mm.
I'm just like,
We
what?
are in winter.
Oh,
Climate
yeah,
change is
bye,
real.
Alec. Thanks for coming.
Bye, Alec.
And actually, yeah, I think I'll cut the recording now. So if you watched, thank you, thank you. See you around.